Uh, Hello everyone, I am Debarshi Chanda, and today I'll be going through the winning solution of the CommonLit Readability Challenge hosted on Kaggle. We will be seeing the general ideas of the solution. So, before moving forward, a little bit about myself. I am an undergraduate at IIT Guwahati. Recently, I received an offer for applied scientist intern at Amazon. Currently, I'm also very active on Kaggle. Currently, I'm a notebooks master ranked under 100 and also an expert in the competitions, datasets, and discussion section. And I'm also an ambassador for weights and biases. So, now coming to today's agenda. First, we will understand the problem statement. Then we'll briefly look into the dataset. It's always good to have a general understanding of the problem statement and the dataset before moving on to solve the problem. And lastly, we'll see the winning solution. So, yeah, let's go on to understand the problem statement. So, the first question that might pop into our head is, what is readability? So, basically, it is a measure of how easy a piece of text is to read. So, it takes into account grammar, spelling, active and passive voice, and many more such things. Now, what's the importance? Why do we need our text to be readable? So, obviously, it's easier to read, it is easier to understand, and therefore, it is good for retention. But also, at the same time, the text should be so easy that the student brain doesn't get challenged, it doesn't develop much. So, ideally, the text should be easy enough to comprehend and difficult enough to contribute to the student's academic development. If we can predict readability properly, it will become very easy for the teachers and the other stakeholders to develop the curriculum properly. So, now that we have understood the problem statement and the impact it has, let's move on to the dataset. So, this is the structure of the data we have been provided. We have the ID column, which is unique for every excerpt. Then we have the URL, which from which the excerpt has been taken. It is also blank in the test. It is blank in the test set. Now we'll see its distribution ahead in the presentation. Then we have the license of the source, which is again blank in the test set. We have the text for which we have to predict the readability. Then we have the target, which is the readability score. And lastly, we have the standard error. So, this can be thought of as the variation among the annotators. This is also not present in the test data. Also, we notice that the training set is quite small, just 2,834 samples. Now, these are two excerpts that I picked from the dataset. On the left, we have a readability score of minus 3.67. This is the most difficult text to read in the dataset. So, if I read it, the commutator is peculiar, consisting of only three segments of a copper ring, while the simplest of other continuous current generators, and so on. So, you can see, right, words like commutator, peculiar. The sentence formation is also a bit complex. Now on the right we have a readability score of 1.71. So this is the most easiest text to read. Now if I read this, when you think of dinosaurs and where they lived, what do you picture? Do you see hot, steamy swamps, thick jungles, or sunny plains? So you can see the difference, right? Quite simple words. So now that we have a fair amount of understanding of the problem statement and the data set, let's move on to the winning solution. So this has been divided into four sections: external data, pseudo-labeling, model training, and ensembling. Just yeah. So Mathis Lucka was the winner of the CommonLit Readability Challenge. So I've linked his Kaggle and GitHub profile. I've also linked the discussion post in which he had described the entire approach. Uh, Also, I've linked the GitHub repository, which contains all the all the code files corresponding to the challenge. Now, this is the distribution of the URLs. So we have articles from Simple Wikipedia, kids.frontiersing.org, Wikipedia, Africanstorybook.org, commonlit.org, and many more. So, if you don't know about Simple Wikipedia, it has Wikipedia articles, but in a simpler language, as the name suggests. So, meaning better readability. So the solution uses script data from the URLs and also some existing data sets. Some of them are available readily available in the Hugging Face datasets library. Now, while gathering external data, we need to preserve the distribution of the data as much as possible, of the original data as much as possible. So, to maintain the length distribution, only sentences with similar lengths were kept, and the rest were filtered out. Now, to maintain the semantic distribution, we are we generate the sentence embeddings the for each excerpt in the training set. We do the same for the external data, and then we retrieve the top five text snippets with the highest cosine similarity score to the original text. So now we have five extra text snippets for each training excerpt. So if you see, this is actually a very clever way to get extra data of good quality. So we all know that data is the more the data, the better. But we also need to maintain quality to some extent. Now let's see a bit of code. So yeah, so I forgot to mention the uh, model that had was used was a sentence transformer. So yeah, so from sentence transformer we import sentence transformer and util. The model name is paraphrase minilm L6v2. So we pass in the model name into the sentence transformer and get the pre-trained weights. Now our sentences are raw text, so we need to somehow convert them to numerical form so that we can do our uh, search. So for that we do model.encode queries and we pass in convert to tensor to true. So we get the encoded queries which are in the form of tensors. So queries here are the original text. Now we pass in the sentences, model.encode sentences. Here the sentences are the external data that we gathered. So we get the encoded sentences. Now we need to do semantic search. So for this we already have a built-in function in the sentence transformers library. We do util.semantic search. We pass in the encoded queries and the encoded sentences, and we specify top k equals 5. So this is since we want the top 5 text snippets with the highest scores and similarity score. So this returns us a list of lists. We have saved it as hits. Now we can understand this as for each of the query, there is a corresponding list in the hits list. Now we iterate over the hits list. So for hit in hits, so this is the structure of a hit. We on the right with that I've shown that a hit consists of 5 dictionaries. Now each of these dictionaries have a corpus ID and a score. So we don't really care about the score. We just care about the corpus ID. So this corpus ID is basically the index of the sentence, the index of the sentence that has been selected. So for this, we pass in a list comprehension. We we iterate over hit, that is this list of dictionaries, and uh, get the h of corpus ID, which gives us the index, and we get the sentence. At the end, we append this sentences to the selected sentences list. I have linked the corresponding notebook here in the below. So I hope that the previous part was I could convey the ideas. Now let's see the pseudo labeling part. So pseudo labeling is basically making use of an of an existing model to label unlabeled data. So getting unlabeled data is quite easier, right? It's cheap, but labeled data is expensive. So pseudo labeling comes in handy. So in this case, we make use of an ensemble of Roberta base and Roberta large to label our external data. But now, to further enhance the quality of our data, the winning solution makes an interesting use of the standard error column. So basically, we use it to filter our pseudo labeled external excerpts. Any excerpt whose pseudo labeled score deviates more than the uh, more than the standard error of the original excerpt is removed. So the models used are again, as I mentioned, an ensemble of Roberta base and Roberta large. Now again we'll see a bit of code. So this is quite simple compared to the previous one. So we define the function filter on def, which takes as input sentences. So these are the external data sentences. Then we take the predictions. So these are the pseudo labeled score by the ensemble of Roberta base and Roberta large. Then we take in the scores. So these are the scores of the corresponding sentence in the original training set, and then we are taking the respective standard error. Now we define two lists: predictions filtered and sentences filtered. Just a minute. Yeah. So yeah, we define a list. We define two lists: predictions filtered and sentences filtered, which we will eventually return. Then we iterate through the predictions. We get the deviation. We get the ground truth. And now we take the absolute difference between the predictions and the ground truth to get our difference. Now, if this difference is less than the deviation, we uh, keep it in our we append it to the predictions filtered, and we append the sentence to the sentences filtered. So in the end, we return both these lists. So I've also linked the corresponding notebook here. So now let's move on to the model training part. So now that we have this entire external data, which is roughly 5 times our original data, we have to make proper use of it. So for this, the solution uses a pre-training approach. Here, we train a model on the pseudo-label data and then evaluate on the entire original training set. Here, we evaluate at every 10 to 60 steps. So steps here doesn't refer to epochs. It rather refers to batches. So for example, suppose I specify a batch size and get a total of 100 batches. I evaluate on the validation set after every 10 batches in case my evaluation steps are 10. So this was widely used in this competition because the training was quite unstable. So we also make use of lower learning rates, 7e minus 6 to 1e minus 5. This is also because of unstable training. The models trained were Albert XX large V2, Debarshi large, Roberta large, and Electra large. Now, for the training approach, we use the previously trained model to fine tune on the original data. So for this, first we make our splits. So we'll divide the training set into 6 folds and train 6 models. Again, here we evaluate at every 10 steps. So this is not recommended. It is generally not a good thing to do, but still it was widely used as it was helping with the leaderboard. Here also we have used low learning rates due to unstable training. The models trained were again Albert XX large V2, Deberta large, Roberta large, and Electra large. So Albert XX large V2 was also trained on the entire data without any evaluation. So this was done because the model training was quite stable for Albert. Also, bootstrap sampling was used instead of cross validation for some of the models. So bootstrapping is basically sampling with replacement. So this means that for a particular training sample might be added once, twice, or even more times. So all this, like first we are using different bird variants, and then we are using different sampling methods. So all this brings diversity to our ensemble, and the more diverse our ensemble is, the more boost we get on the leaderboard. So now again, we'll see a bit of code, a lot of code actually. So this is the sample code of how our entire training pipeline would roughly look like. So this is for the Albert large XX large V2 model. So first we define our training configuration. So we set the seed to 28. Num labels is 1 since it is a regression problem. The epochs is set to 5. Batch size is 3. The learning rate is again quite small, 9 into 10 raised to minus 6. Weight decay is 0.01. Logging steps is 60, so this is the frequency with which we evaluate on the validation set. Model name is Albert XX/V2. Hidden dropout is 0.07 and attention props dropout is 0.1. So these are basically the attention in the transformer layers. And actually, a lot of the other top solutions set the hidden dropout and attention props dropout to 0. So it turns out that dropout isn't optimal for regression problems. So it actually worsens the performance. So in our solution also, these values are actually quite low, if you notice. Then we set the max length to 256. Now, moving on to the imports. So all the imports are from the transformers library. Actually, the transformers library makes model training quite easy. You already have a lot of inbuilt stuff. So now from transformers we import auto model for sequence classification, auto tokenizer, and auto config. Then we import the training arguments and trainer. We will see what they do in a while. Then we import the Adam W, which is the optimizer, and we import get linear schedule with former, which is the scheduler we will use. Now, just a minute. Yeah. So now let's see the processing part. So first we have to get the tokenizer. So we have to somehow convert our raw text to numbers, so to feed into the models, right? So we instantiate the tokenizer, the auto tokenizer class. So from auto tokenizer dot auto tokenizer dot from pre-trained, we pass in the model name. So now we have a pre-trained tokenizer for Albert XX large V2 model. Now that we have our tokenizer, we convert our trained data to encodings. For this, we call the tokenizer, pass in the trained data, and the trained data truncation equals true, padding equals true, and max length. So we have passed padding equals true. So what this does is that in case the length of our text is greater than the max length, it simply truncates the text till the max length is till the specified max length. We have also set padding equals to true. So uh, this is for the case when the text length is less than the max length. So here we add a padding token till we reach the specified max length. Now we get the train encodings. We do the same for the uh, test data and get the test encodings. Now lit dataset, it is actually a user-defined class. So I haven't shown it here. What this essentially does is that we pass in the train encodings and labels and get the dataset object. We do the same for test encodings and test labels. Then we get our train data loaded. We define the training steps to be length of the training data loader into the epochs. So length of train data loader is actually the number of patches. So we multiply it with epochs to get the total number of training steps. Then we have the warm-up steps, which is the ceiling of training steps into 0.06. So we will use warm-up steps in our scheduler. So what happens when we use get linear schedule with warm-up is that we first increase the learning rate linearly till the specified warm-up steps, and then we decay the learning rate linearly. So we have the training arguments here that we put it earlier. So we pass in the output directory. We pass in num train epochs to epochs, which is the total number of training epochs. Then we set the training batch size. Then we specify the login directory to store the logs. Then we specify the logging steps, which is number of steps after which evaluation will take place. Then we pass in the seed. Uh, then we pass in the weight decay and the learning rate. So now we have to get the configuration file. So what we have to do is autoconfig.from pre-trained. Then we pass in the model name for which we want the configuration file. We pass in num labels. So this essentially will modify the head of the model. So then we pass in the hidden dropout and the attention props dropout. So now we have the configuration model configuration, right? We want to get the model architecture. So for this we use auto model for sequence classification. Dot from pretend we pass in the model name and the model config. Now we have the model. Now we get the optimizer, that is Adam W. We pass in the parameters and the learning rate. We get the scheduler. We pass in the optimizer, the number of training steps, and the number of warm-up steps. Now we don't have to do much. We instantiate a trainer. We pass in the model, the training arguments that we defined above, the training dataset. Then for the optimizer, we pass in a tuple of optimizer and scheduler. Callback, so this is optional. Eval callback is a user-defined callback that Mathis had mentioned in his notebook, so I mentioned it here. Now, to start the training, we just do trainer.train. That's all for the training part. So now let's move on to the ensembling part. Sorry, and yeah, I've also mentioned the corresponding notebook here. Yeah, now let's move on to the ensembling part. So here, so first we generate an OOF dataset by getting predictions on the validation set for each of the foods. So, so when we initially split the data into six foods, we had six validation sets and we had trained six models. So now we can predict on each of the validation sets and generate this out of full data set. Now we divide this out of full data set into six new folds, and now we train six ridge regression models. So the final submission consists of two of the ridge regression models trained above, one bootstrapped model that I had mentioned earlier, uh, one Albert XX large model that was trained on the entire data without evaluation. Uh, so the weighted average was taken for aggregating these predictions, and weights were chosen based on the public leaderboard and the intuition. So this is again not recommended. So, this tends to public leaderboard overfitting. So yeah, and I have again mentioned the corresponding notebook here. Yeah. So thank you. That's all from my side. I hope this session was useful for you all, and you all got to learn something new. Here are some of my socials. You can connect with me here. Uh, I'm on LinkedIn. You can find me using this URL, linkedin.com/in/slash Debarshi Chanda. You can also follow me on Kaggle. I keep publishing kernels. I have also recently joined Twitter. You can find me at twitter.com/dchanda underscore. So that's an underscore at the end. Thank you.